Okay, welcome to lecture number 61. In this lecture, basically we are going to learn how to divide any segment in whatever ratio we want, internally as well as externally, and then we are going to look at one very important theorem, Peroneus Circle theorem, and I have got the diagrams made for that. So first let us understand. Suppose I have been given a segment, say AB, and I want to bisect it. I want to find the midpoint of it. I mean, there are many methods. You can draw perpendicular, bisector, etc. But let us develop a method. You draw a segment perpendicular here, and exactly same length segment if you draw perpendicular other side, and if you join them, by similarity you are going to get this as a midpoint. Right? And now at the same time, okay, suppose I want to do it in the ratio 2:1. Suppose 2:1. Then I draw this one, double that of this, and then join. Then I will get the trisection point here. P will be trisection point because this is 2:1. This will be 2:1 by similarity, because both the angles, vertex opposite angles are equal, and 90 degree we have created it to be equal, and therefore I can divide actually the segment in whatever ratio I want. Now suppose I want external division, 2:1. Now C point is 2:1 internal division, and I am looking for external point, which is AD upon DB is also 2:1. Then in that case what we do is we just shift this segment from this side to the other side, and again the similarity will work for us, and when we join these two we get this point, which is D, and you will find that AD upon DB is 2:1. So this is a nice method and a quick method of dividing any segment in whatever ratio we want. Suppose now a segment K is given to you and segment 1 unit is given to you. These two segments are given to you, segment of length K, and it could be root 2. K is equal to root 2, and this segment is of unit length, which is 1. Then segment AB can be divided in the ratio K:1. If you make this stand here and 1 unit stand here, you join them, you get the external division. 1 unit, if you make it stand upside down here and join the endpoints, you get internal division of segment AB in the ratio K:1. We will require this division many times, and therefore learning this technique of dividing any segment in whatever ratio we want, K:1, K can be any real number, can be acquired. So this is what is the procedure. It is very nicely explained in the lecture note number 61. Now let us get into the theorem, Peroneus Circle theorem. Basically Peroneus Circle theorem says that by angle bisector property, if I draw angle bisector of angle APB, say it intersects AB at C, internal angle bisector, and external angle bisector if I draw of angle APB, it intersects line AB at D, then angle bisector property says PA upon PB is equal to AC upon CB for internal, and numerically this is also going to be AD upon DB. This property we have proved when we learnt angle bisector, internal and external, and their properties. Now if I want to find out all points P in this plane which possess the ratio K, which is AC upon CB, for example, any ratio that I create, I want PA upon PB to be having ratio K. So PA upon PB is equal to K. Then by this method I can get point C, which is internal division. I can get point D as external division, which is AD upon DB is equal to K, and then the claim is, the Peroneus Circle theorem says that all the points on the circle with CD as a diameter will also give you the ratio PA upon PB is equal to K. That is very important. Now, if I generally take, so I draw semicircle, and exactly similar thing will happen in the remaining semicircle also. And now I take any point P on the semicircle and join it with A and B. And I just want to check whether every point on circle with diameter CD will behave exactly same or not. And I find PA upon PB is equal to PC upon PD. That is what, suppose if I take point on the circle, then this angle is going to be equal to this angle by angle bisector property, converse of angle bisector property. If PA upon PB is equal to AC upon CB, then this is, suppose I take any point and draw angle bisector, then this point will be C, this point will be B, and I draw external angle bisector, I get point D over here. And then I want to show that point P lies on the circle with CD as a diameter. Okay, so if point P, internal angle bisector is C and external angle bisector is D, then that means these two angles are equal and these two angles are also equal. That means the angle subtended at P with C and D will be 90 degree. X plus Y happens to be 90 degree, and all those points P which will subtend 90 degree with C and D will give me exactly same ratio, which is AC upon CB or AD upon DB, which in this case is PA upon PB, which is equal to K. So if I fix this ratio K, I will end up getting a circle on which if I take any point, that point will give me PA upon PB is equal to K. Now this is important theorem because in constructions we will be given many other times the ratio of the sides. PA upon PB is say 3:2 and the height of the triangle is given. Then Apollonius circle is going to be one of our locus for finding out point P, and that is why this particular locus is important. So what we have done is, basically if the ratio K is given to us and the segment AB is given to us, then we are claiming that if we first we have to find out internal division point C, which we can do it by this method, external division point D, which I can do it by this method, and draw semicircle using CD as a diameter. Then the claim of this theorem is every point on that semicircle or maybe circle will give us ratio PA upon PB exactly equal to K. That is what we have proved, and it is a simple proof because internal angle bisector and external angle bisector both, if we add 2x plus 2y becomes 180, and therefore x plus y becomes 90, and the locus of point P which subtends 90 degree with CD is going to be the circle. That is the proof. However, converse of this is also true, and the statement of converse would be, if I give you PA upon PB is equal to AC upon CB is equal to AD upon DB, then the angle CPD is going to be 90 degrees, and therefore the point will lie on circle. Okay, so in this case now the point is randomly chosen in the space such that PA upon PB is equal to AC upon CB is equal to AD upon DB, and now we are supposed to prove that point is on the circle. So the converse is little difficult. So it is given that PA upon PB is equal to K. So PA upon PB in this diagram is equal to K, which is also equal to AC upon CB, which is also equal to AD upon DB. And one genius construction is being done. Draw line through B parallel to PA. So basically this line is parallel to P. Once we draw parallel line in any configuration, we end up getting some similar triangles. So in this case, you see the first similar triangle that we get is CPA. Triangle CPA is similar to triangle CRB. And if we write ratios, proper ratios, then I will get AC upon CRB AC upon CB, that is the first ratio, which is equal to PA upon RB. That is what I got. I have written here, PA upon RB. Now if I take another pair of similar triangles, which is DPA, triangle DPA is going to be similar to DQB, right? And again it will give me ratio AD, which is AD upon DB, AD upon DB, which is this ratio, which is PA upon PB, AD upon DB, which is again going to be equal to PA upon QB, PA upon QB, and in the given connection it is PA upon PB. So here AC upon CB happens to be PA upon RB, PA upon QB, and PA upon PB. Therefore RB, QB and PB, they are equal segments, which means RB is equal to RQ is RB is equal to QB is equal to PB. That means if I take B as a center and draw circle, then P will lie on semicircle, and therefore angle between C, P and D is going to be 90 degrees, and therefore point is going to be on semicircle. So this is Apollonius circle theorem, and this is its converse, which gives us in constructions, which gives us one more additional locus where we can solve problems when say for example CS to B ratio is given, angle A is given, and length of BC is given. So that is one construction problem which we are supposed to do in this particular lecture, and that is what we will do. Now we know how to get the locus when the ratio of sides is given. Okay, so what is given now? Given capital A, small a and CS to B. Okay, so we start with small a. We divide this in the ratio CS to B. We draw semicircle. This is first locus of A. This is B and C. First locus of A. And now we want capital A, inscribed angle to be capital A. Therefore, we draw perpendicular bisector of BC, and we draw, say, auxiliary figure. This is going to be my circumcenter. If the angle is A, then this angle is going to be 2A, right? And therefore, if that angle is going to be 2A, I need to have this angle, which is equal to 90 minus A. So I draw 90 minus A here, this segment, and draw perpendicular bisector, that gives me circumcenter, and I draw another circle, and every point on this circle will give me angle equal to capital A. Every angle will be capital A. So this is one locus of capital A, which gives me angle capital A, which is given to me. This is another, Apollonius circle is another locus of capital A, and hence you end up getting actual point capital A in this construction. Now, having given CS to B, unless we have Apollonius circle locus, we will not be able to complete the construction. Now, the next construction is capital R, small r and A in this particular lecture. Now, capital R, small r, capital R, then A and small a. Out of these three things, if you are given only two, we can find out the third. The way here it was capital A and small a was given, and we have found out what should be the circumradius of this circle. Similarly, now capital R and capital A is given. In this case, capital R and capital A is given, so we should be able to find out small a. How do you do that? You draw a circle with capital R as a radius and draw any angle anywhere as capital A. Then these 2 points will give you distance BC, small a, right? So you can start with small a or you can start with capital R circle. Then as I said, you can draw any angle which is capital A, and therefore you can fix BC. Okay. Now one locus of small r is going to be lying horizontal to parallel to BC at distance small. Now suppose the incenter of required triangle is, here, then this is what is going to be my auxiliary construction. Then this angle will be copied here, and then you will get actual point A. But then how do you decide on the parallel line at a distance r, which is the point which is going to be incenter? Now again, here I use properties of the triangle. Now if this angle is capital A, I know major angle BIC is going to be 90 plus A by 2. We have proved this earlier, and therefore now I know that angle BIC is again going to be 90 plus A by 2, and therefore by the similar construction I construct angle. How do I finish the construction now? I draw perpendicular bisector, which is already there, and then I calculate the circumcenter. Suppose now I am interested in this particular locus, which is locus of I. Locus of I will be this arc, and then we are supposed to find out that arc. If we remember the property that the internal bisector, angle bisector of A, perpendicular bisector of BC, and circumcircle of ABC will be concurrent at L. So you take L as a center, take LB as a radius, and draw an arc, which that arc will intersect this horizontal line at 2 points, and those 2 points are going to be your probable incenters. Once you get incenter I, you copy that angle to the other side to get A on circumcenter. Now this is a little involved construction, because you are required to do two different things for getting locus of I. First, you are supposed to get a locus of A, which is circumcircle, because our capital R and small r, capital A is given. And second, you have to get locus of I, and in this problem, in this description, the locus of I is done by some other method, but I am discussing right now that if you get point L, which is perpendicular bisector of BC and circumcircle ABC, note that this circumcircle ABC will continue to remain same. We have not fixed point A. Point A is required to be fixed. We started with some other point A to get BC, but that is not our final point A. We will get final point A after completing the construction of I and then copying the angle. So get the point L. We know LB is equal to LC is equal to LI is equal to LI1. L happens to be the circumcenter, and therefore you draw circle. That circle intersects the line parallel to BC at I, and there will be two intersections. One is therefore there will be two triangles which are possible. Okay, just go through lecture number 61 and you will find that whatever we discussed is properly noted in that particular lecture. Go through it and try to do the homework which is given. See you in lecture number 62. Thank you.